Welcome back to section 4.1, page 4. So in this example, we're asked to determine if the sequence of letters forms a path. If it is a path, record the length. If the sequence is not a path, state the reason that it fails. So remember, if we look back to our definition, what does it mean to be a path? A path is consecutive edges and no edge is repeated. Okay, so let's try. So for this one, it says go from A to B. So I'm going to just draw a line here, A to B, and then from B to C. So they're consecutive, nothing's repeated. So we would say, yes, that is a path. And what is the length? Well, how many edges do we have there? Length equals 2. 1, 2. Okay, go on to part B. So here we're starting out and we're going from A to B again. And then we're going from B to C, and then we're going from C to D, and then we're going all the way around back to D again, all the way around that circle. So again, we did have consecutive edges. Nothing is repeated, so we would say it is a path. And what is its length? Its length equals 1, 2, 3. That was one whole 4. Okay, length of 4. So now let's try this last one here. So we go ahead and say, well, we're starting from A and going to B. So 1, B to C, 2, C to D, 3, around D, okay, 4, and then what are we doing? We're repeating here. I don't want to make those look like they're connected, so let me just do that. Oops. So here and then here. Okay, those were two separate pieces. All right, so what do we see there? To fix that. Okay, so we can see that we had a repeated edge, so it's not a path. Okay, because CD is a repeated edge. Okay, so let's go on and read the next example. It says, can you find at least 3 paths from A to B, and what are their lengths? Well, obviously the simple one is just to go from A to B like that. So we would call it AB, and we would say its length is 1. Okay, so let's do another one. Well, maybe we go to C like this, and then back that way to B. So that would be, we would call that A, C, B, and its length would be 2. Okay, and then what's another way we could go? Well, we could go all the way around this way. So that's one way to get to C, and then back to B. Okay, so that's also A, C, B, but a different path, and a length of 2. Okay, so now go ahead and pause the video, try both paths and their lengths and finding paths, classwork E and F, and then come on back. Okay, so we're looking at the classwork now, and the bottom of this page here you can see classwork E, where you were supposed to determine if it was a path. So when we did C to D to B, what was that? That's a path of length 2. When we did this one here, we were going from D to F, so D to F, and then to A, okay, and then to E, and then to F, and then back to D. That's a problem, right? Because we're repeating a path. So we said, nope, it's not a path. We repeated the edge DF. And the last example, we went from D to F, and then to A, so this side. Now notice we didn't go that way or we'd have E in there. And then E, and then F. So this one here, nothing's repeated. How many edges do we have? 1, 2, 3, 4. So length of 4. Okay, so let's turn the page and look at F here. So when we look at F, it asks for at least 3 paths. Well, you can do it however you want, but the way I did it was from A to D. Here's one example. That's probably the simplest one. okay, and it's of length 1. And then another way I did it is I went from A to F, and then from F to D. Now, some people label them like this, 1, 2, so you can see the order that you're doing things in. Another way to do it is to go from A to E like this, and then from E to F, and then from F to D. Okay, so 1, 2, 3, length of 3. All right, so let's go back to the handout and take a look at some definitions. So definition, a path containing all the edges of a graph is called an Euler path. So all the edges. An Euler path that begins and ends at the same vertex, that's called an Euler circuit. So a path just, is a path, but a circuit means it closes, it starts and ends at the same place. A graph with all even vertices containing an Euler circuit is called an Euler graph. So that would mean everything is even and we begin and end at the same place. That's called an Euler graph. So we've got two theorems that are going to help us to determine whether or not a graph is traceable. Euler's path theorem. If a graph is connected and has 0 to odd vertices, then it has an Euler path, meaning you can trace it. The path must start at one of the odd vertices and end at the other. If the graph has more than 2 odd vertices, then it cannot have an Euler path. It's not traceable. Okay? Now, if a graph is connected and every vertex is even, then it has an Euler circuit or it's traceable. Okay, so it's connected and every vertex is even, then we know it's a circuit. If the graph has any odd vertices, then it does not have a circuit. So remember, circuit means starts and ends in the same place. Okay, that ends page 4.